apply the limits. Before apply, yeah, you can apply the limit now. So if you apply the limit, what will we get? N tends to infinity. What will happen? Huh? When square and everything is done, we are now doing this. Log n and square root of, oh, it is square root here. Okay, got it. So, to differentiate this, sorry, before that, if you apply the limit as it is, what happens? Log infinity is infinity. Square root of infinity is infinity. So, we get infinity over infinity. That's what? Non-deterministic, right? You should have studied in your math class. So this should be then your ideal case for differentiation. So you have to differentiate the numerator and denominator separately. So I already went over differentiation of log n, right? So what can you say about this? Limit n tends to infinity. Differentiation of log n to the base 2 is what? Differentiation of log n to the base 2. Log e to the base 2 times 1 over n. If you don't want to memorize this, do it out, work it out a couple of times. You should get it. Okay? So 1 over n should be always there, right? Because differentiation of log n is 1 over n times constant because of this base. If it was base e, log n to the base e differentiation is just 1 over n. Because of this different base, we have that constant term. But we need that constant here because we'll see why. Right? So this is 1 over n times what? That's it, right? Then what about the denominator? Remember, when you do L'Hopital's rule, you have to differentiate them separately. Numerator separately, denominator separately. So denominator is square root of n. So how do we differentiate that? Square root of n is what? N to the power half, right? This is what square root of n is. So now we have to differentiate this. So half times n to the power half minus 1. And then of course differentiation of n with respect to n is a 1, right? Like I showed on the top. So that's why we are not bothered about this 1. Okay? Clear? How to differentiate n to the power half? The exponent comes before half times n to the power, the exponent again is half minus 1. That's basic differentiation. Times differentiation of whatever is of a function. The function itself is n here with respect to n. So differentiation of n with respect to n is 1. Okay? So what is this now? If you want to simplify this, let's simplify that. This is equal to limit n tends to infinity log e to the base 2. You see here this 1 over 2, if I take it to the numerator, can I take it? What happens? It becomes 2, right? So the whole thing, this 2 can be clubbed with that log e to the base 2, grouping all my constants together. So this 2 goes to the numerator, 1 is half, right? 1 over 1 half, so goes to the numerator, so 2 log e to the base 2. So then I am combining all my n terms. So you have 1 over n divided by n to the half minus 1, which is n to the power negative half. Half minus 1 is negative half, right? So what happens? Now you see here this n can be brought with this, right? Because 1 over n to the negative half, right? So this could be written So you can say this is 2 log e to the base 2, limit n tends to infinity, 1 over n times what? N to the negative half. I'm taking my constant out and writing it as limit n tends to infinity, 1 over n, n goes to the denominator times n to the negative half. So what is this? N times n to the negative half is what? N to the power 1/2, right? Because this is n to the 1 and you're multiplying, so n to the 1 times n to the negative half is 1 minus half in terms of the exponent, so that's equal to half. So I can write this as what? 2 log e to the base 2, limit n tends to infinity, 1 over n to the power half. What is that now when you apply the limit? 1 over n to the half, when you apply the limit, it is 0. Why? When you apply the limit, right? 1 over n, so when you apply the limit 1 over infinity basically. Infinity, square root of infinity is also infinity. So 1 over infinity is 0. That means the whole thing will be what? Anyone this side. 2 log e to the base 2 is here and then you have 0, right? So the whole thing is 0. So whole thing is 0. So what do you get? Our limit, this thing is 0. If this is 0, what can we conclude? Which one grows faster, or they grow at the same rate? Which case it is? Which one grows faster? Denominator, right? Because if you get the whole thing is equal to 0, you're dividing something by a very large value, that's why it is tending to 0. So denominator grows faster. So that's the case of what? So f of n is always less than or equal to g of n. This definition holds good for which one? Big O or theta or omega? Big O. Okay? So f of n is always bounded above by some function, big I. So g of n is always bounding it up greater above. Okay? So we can say what? What is our f of n? Log n to the base 2 is big O of square root of n. Which means what? Square root of n grows faster compared to log n. Okay? So log n is pretty much the slowest function you will see. Okay? So you can now see which one between the two, even though it looks like a little difficult to find, but you do this L'Hopital's rule and all this thing, we can now surely say square root of n grows faster. Okay? Clear? Okay, so there are a lot more problems, similar problems I have listed here, so you have to practice. So some more here, all this thing. Now let's do one from here. So when you have to apply L'Hopital's rule, two kinds of problems. Like this, I'll give you two functions, ask you to find how they are related, very similar to this. Take lower limit, if it is infinity over infinity or 0 over 0. You know when you should apply L'Hopital's rule, the differentiation, right? To get 0 over 0, you have to differentiate the numerator denominator separately because 0 over 0 is not defined. Similarly, if you get 0 over infinity is what? Not defined. Infinity over 0 or infinity over infinity. So you should do your differentiation if you get like this when you apply the limits. Okay? After the first differentiation, if you still get like this, you have to again differentiate. You know that, right? From calculus. You may not get the answer right away. You may have to do more than one differentiation. Okay? So that is one kind of problem. The other kind of problem is, like we did before, I will give you just one function, like a square root 3n squared plus 7 and so on. Ask you to find the big O function of it, or the theta or the omega. Right? So in both cases, you have to use the L'Hopital rule. From now on, we will try to kind of proceed a little faster by not going through L'Hopital's rule, but by using all our experience that we have gained so far in trying to find out the most dominating term in a given expression and stuff like that. Okay? So what we'll do is, we'll start with some simple stuff and then we'll do the other ones over there. Let's take up this thing that we have. 3n squared plus 7n plus 4. Now what I'm going to do is, I'm going to write each of this as a theta. Okay? So I'm interested now more on theta, and that's what we'll focus mostly now. That's how this goes. So if I want to write this as theta, what can I say? This 3n squared is theta of what? n squared, right? So that's our experience. And we can do that or verify this using our L'Hopital's rule. But we're not going to use L'Hopital's rule in this case. Right? So these are, I told you what kind of problems we have to use L'Hopital's rule, right? I'll explicitly ask you to find big O, theta or omega and verify it or show using, or show, proof, things like that. I won't say L'Hopital's rule, you have to know you have to use L'Hopital's rule, that's the only rule we have seen, right? The other cases, given two functions, you have to find how they are related. So now what we are going to do is, just given a polynomial, I want to quickly say what is the theta. If I don't ask you to show or prove, you can do something like this. This is what? N. This is, you can say as a constant. 4 is a constant. So if I want to write the theta for a constant, I can say theta of 1. Okay? So now basically, you have three functions that grow. One grows at the same rate as n squared, the other grows at the same rate as n, the other grows as a constant. It doesn't grow much. Right? So between these three, which one is dominating? N squared. Right? So I can say this is theta of n squared. We have seen this already. Remember the theorem that we proved last class? That's the theorem, right? Theta of n squared plus theta of n, and then we take the maximum of functions. Here the maximum of n squared and n is n squared, right? So the theorem we have to know how to prove, like we did last class. That's also a question. Okay, but we are just using the theorem here. So what can I say? Theta, the whole thing is now theta of n squared. Okay? Clear? Can I erase this side? Yeah. So let's take up that log n over there. So we have what? 2n log, if I don't, again as I said, if I don't specify the base, it's the base 2. So log n plus 2 square plus n plus 2 whole square log n over 2. Now, let's see how many of you know this. Are this the same? Log n square and log square n. Log n square and log square n. Oh, this is the same or this one?
Well, is it in the base?
Huh?
Is it in the base?
No, it's not in the base. No, it's not in the base, it's here.
That's 2 square roots of n squared. You know, it's a square root of log, right?
Huh?
Well, one's the square root of n and one's the square root of log.
Square root of n, where square root is coming?
I'm sorry, square of n.
Square of n, yes, and this is?
Square of log.
Right. So this is equal to log n times n. is equal to log n times log n. Alright? You know that, again from calculus, or college algebra, whenever these are logarithms, if you have log n square, can I say this is 2 times log n? You can bring the exponent n square something, right? Can be written as 2 times log n. You cannot write the other one. You cannot write log square n as this. That's not right. But you can say log n square is 2 times log n. You know this? If you don't know, at least you know now. Okay? So, we are going to make use of this property here. Okay? That itself leads to an interesting comparison. Now, is anyone interested in knowing which of these two grow faster? Can anyone say which one will grow faster? Okay, so we have to verify it, right? So we have a tool to verify. So let's skip this for a time being. This problem will do this. How will we verify which one grows faster? We just did some problems, right? Yes or no?
Yes.
L'Hopital's rule. We want to compare the two functions and find out which one grows faster. That's the only rule we have, right? So let's do that. Let's let our f of n be this, and our g of n be this. So let's try to do this. Limit n tends to infinity, f of n over g of n is what?
Log n squared over log squared n.
Log n squared over log squared n. So before you apply the limit, if you apply the limit, of course you'll get infinity over infinity, right? But using what I said, you can try to simplify that, right? Log n squared can be written as 2 times log n, and my log square n remains the same. Okay? Here? So now log n is log square n is log n times log n, right? So I can apply that here and say this is 2 times log n divided by log n times log n. So I can simplify this further. Wow, oh, log n cancels out, right? So it is equal to 2 over log n. Okay? So now it comes out to limit n tends to infinity, 2 over log n. And can anyone say what is this? 2 over log n, if you apply the limit, 0. Because log infinity is infinity. 2 over infinity is 0. So we get the limit as 0. So what can we say? Which one grows faster? G of n grows faster, right? So what is our f of n? F of n is log n square is what? Huh? Big O of what? G of n, which is our other function, log square n. So between the two, which one grows faster? Log square n grows faster compared to log n square. Basically, why? Because you have here what? Log n square is 2 log n, right? And even like here, if you know again logarithms, right? Log a times b is what? Log a plus log b, right? So log n times n is what? Log n plus log n. So if you are still confused how it is 2 log n, this is how it is 2 log n. Log n times n is log n plus log n. Log a times b is log a plus log b. Here a and b are n. So log n times n is log n plus log n, which is 2 log n. That's why it is 2 log. Okay? So this is a log n term, and this is what? A log n times log n term. So that's why this term grows fast. Okay? Yeah? You should know how to do this too. Alright, so now let's go back to our original problem.
Can't you just look at that problem and tell that one was bigger than the other one?
What?
I mean, isn't it obvious that log...
It is obvious, but you have to use this tool.
Oh, okay.
Right, and I want you to show, you have to use L'Hopital's rule to show. Right? In this case, we will go with the obvious thing that you are talking about, because I don't want you to show here, I just want you to find this in terms of theta. Right? So let me write this again. What is that? 2n log n plus 2 square plus n plus 2 square log n over 2. So, I want to use like term by term simplification for write them as theta terms and then simplify overall the whole expression. So I want to simplify this and then simplify this and then combine it. Right? So let's try to write this in terms of theta. So what this can be written? Like this is what? Log n plus 2 square, right? So how can this be simplified? This is equal to what? Log n squared. The 2n is as it is. What about log n plus 2 square? Log n squared. 2 times log n plus 2. Like instead of n, we have n plus 2. That's all, right? So when we say log n square is 2 times log n, log n plus 2 square is 2 times log n plus 2. We have n log n square is 2 times log n. So instead of n, we have there what? N plus 2. That's the only thing. So instead of n, we have n plus 2, so I can subtract like this. Okay? Yeah? So now what is this? 2n times 2, which is equal to what? 4n log n plus 2. So you have to now know this. Log n plus 2 is what? Same as almost log n, right? So what I can do, this is theta of what? Look at the n terms. We have an n and then log n, right? So this is theta of n log n. 4n times log n plus 2. So this is theta of n log n. If you want, you can verify using L'Hopital's rule. You should get a constant, right? Because it's theta. So if you do the limit and everything, you probably get that 4, which is a constant. Okay? So as a practice, you can do that, even though it may sound obvious for some people. Okay? So until you master L'Hopital's rule, taking the limit and everything, you can do this. So this is theta of n log n. So let's try to simplify this. How do you simplify this? N plus 2 square times log n over 2. So this is what? Log n divided by 2. I can say this as what? This is n plus 2 square and equivalent to, in terms of very simple term, what is the equivalency? You'll start thinking on those lines, n square, right? So I can say this is theta of what? N square log n. N plus 2 square grows at the same rate as n square. Log n over 2 grows at the same rate as log n. So I'm looking at each of these individual terms within this. N plus 2 whole squares grows the same rate as n square. So that's theta of n square. And then log n over 2 grows at the same rate as log n. So I can combine them and say this theta of n square log n. Alright? Okay? So now looking at these two, what we have, the first term is theta of n log n. The second term is theta of n square log n. So between the two, using our original theorem, which one grows faster? This is n log n, this is n square log n. So which one? N square log n, right? So that's our theorem. N square log n grows faster. So this is the theta for this expression. Okay? So you should know how to simplify this. So then we have the small other one, which is what? 2 to the power n plus 1 and 3 to the power n minus 1. How do you find out this? N is an exponent, right? So of course then our answer would be something's exponent, theta of something, right? So what we'll try to do is what? We want to get rid of this n plus 1 term and this has some n term, right? So I can say this is 2 raised to 2 to the power n, right? 2 to the power n plus 1 is 2 times 2 raised to n, right? Multiplication. Plus, what about this one? Since it was an n plus 1, we multiplied by 2. This is n minus 1. So, what? Yes, proceed.
Divide.
Divide by
3.
3. So you have n minus 1 on the exponent, so it is divided by, because to account for this negative 1 over 3 times 3 to the n. So now I can say in terms of theta, the first one is going to be what?